Imagine a dense, interconnected system where a single critical pathway is suddenly severed. Energy immediately reroutes, violently cascading into secondary, unequipped threads. In the mid-20th century, mathematician Stanislaw Ulam proposed what would become the Kelly-Ulam reconstruction conjecture. The premise poses a direct question. Can you perfectly recreate an entire massive network using only isolated, incomplete fragments of its structure? This animated diagram illustrates a mathematical deck. For every vertex in the parent graph, the system generates a unique card. Each card represents a vertex-deleted subgraph. It displays an identically detailed version of the network, but with one single vertex and its connecting edges entirely deleted. The mathematical mystery is whether these blinded, localized perspectives contain enough overlapping data to prove the undeniable layout of the global whole. A 2026 paper by A.S.
Pirolo tests this limit by extracting a highly specific edge metric from a Kelly-Ulam deck. This animation illustrates that metric, topological friction, represented mathematically as the capped alternative path action, or S of E. If a specific connection vanishes, this metric calculates the exact length of the absolute shortest detour through the surviving network, capped at a practical search horizon of 10. Pirolo's primary thesis demonstrates that extracting this exact routing data from a standard general Kelly-Ulam deck is completely impossible. The mathematical phenomenon responsible for this failure is called the entanglement obstruction. Accurately calculating global routing from isolated data requires a precise accounting of how local subgraphs misrepresent their own geometry. This image displays the central algebraic identity of the paper, the master deck equation. The left side represents the brute force summation. It counts every instance where an edge's path matches our target length across the entire deck. The first term on the right is the ideal mathematical state. Perfectly tracking an edge across the deck should yield a clean, predictable linear multiple. But the reality of the calculation introduces the final term, omega k, the entanglement obstruction. Omega k isolates the exact deviation from the ideal, the strict numerical tally of every overcount and undercount generated by the isolated cards. This term is not a random glitch. It is the mathematical manifestation of vertex-deleted subgraphs actively misreporting their own shortest paths. The most common structural failure driving the omega k error is the false shortcut. This diagram highlights an edge with two viable detours, above a tight 3-node triangle, below a winding 5-node path. When the top node is deleted to create a card, the short path vanishes entirely. The card now relies on the bottom 5-node route. This isolated card now falsely reports the alternative path as being much longer than it actually is in the global network, corrupting our count. In an experimental dataset of 10,000 networks, Pirolo detected 50,601 instances of this exact geometric ghost. The second major mechanism breaking the equation is geodesic multiplicity. This occurs when an edge possesses multiple, distinct alternative paths of the exact same length. If a node is deleted from the top route, the bottom path flawlessly survives. This tricks the deck into overcounting the edge's survival rate across multiple different cards. Unless we can mathematically eradicate these hidden errors, any global path calculations derived from local decks are structurally contaminated. The question then becomes, how do we force the omega k error term to absolute zero? The paper proposes a structural solution, limiting the scope entirely to neck-conditioned graphs. The first requirement is high girth. This means the graph inherently lacks small, tight cycles. By enforcing high girth and removing these tight loops, deleting a node can no longer reveal a hidden, longer path. The false shortcut error mathematically drops to zero. The second requirement is geodesic uniqueness. Every edge must possess only one absolute shortest alternative path. This rule outlaws the symmetrical duplicate routes, eliminating the overcounting caused by geodesic multiplicity. With these two conditions met, the entanglement obstruction, omega k, is completely annihilated. By strictly constraining the graph's topology, the blinded, localized views of the deck become perfectly aligned with the global reality. When omega k hits zero, the master deck equation collapses into a clean, exact reconstruction formula, allowing perfect global pathing derived directly from local cards. We can see the immediate utility of this proof in hardware engineering, specifically within RISC instruction scheduling. Inside a standard 128-bit SIMD pipeline, the dependency graph of instructions naturally features low register density. This animated graph shows how compiler instruction windows organically and perfectly satisfy the exact net conditions required by the theorem. A compile time scheduler uses this math to categorize instruction flexibility. An edge with a friction value of 3 indicates a 2-hop alternative, meaning instruction reordering is perfectly safe. Conversely, an edge in the cap of 11 denotes a critical bottleneck that cannot be bypassed. Pirolo's proof provides a zero-overhead, mathematically guaranteed certainty for alternative path routing, moving beyond the heuristic guesses used in legacy scheduling. This theoretical framework also extends to the machine learning industry, enabling the deterministic pruning of sparse neural networks. The intricate layers of an artificial neural network seamlessly shed dead connections, revealing a sleek, highly optimized inner core. Operating under net conditions transforms the NP-hard problem of finding redundant network pathways into a strictly computable polynomial algorithm. The 70-year-old Kelly-Ulam Conjecture asks if a system can be understood purely through its fragments. The historical barrier of path length reconstruction finally vanishes once the topological friction obscuring the deck is surgically eliminated.